So now we're going to move on to our second example. So in our second example here, we're trying to maximize the volume of a box, okay? And so we assume here that ABC Airlines has a policy that states the baggage must be box shaped and its sum in height, width, and length must not exceed 72 inches. And so here's why I have this equation down here towards the bottom of the box here. This one right here. Okay. So we see we have a width, another width, and a height. Okay. And so this plus that has to be 72 inches. Okay. We also know here, just by knowing that we're dealing with a rectangular box, that the area of the box will be length times width times height. But since the length and the width are the same measurement, then we just use W for both. Okay. So looking at this question here, with the constraint of all three sides here must total to be 72 inches, we want to find out the following. First, what dimensions, length, width, and height would give the max volume? And what is the max volume? So again, this will be another type of optimization problem. Okay. And so to start this off here, we notice, let me come over here, that the volume here is W squared times H. And we want volume just in terms of W. So if we want to find a function, just V of W here, then what we're going to have to do is rewrite this perimeter, well, not perimeter, but rewrite this particular constraint equation to where it's just H equals something. And so here, if we were to subtract 2W from each side, we will see that H would be 72 minus 2W. Okay? And so with that being said, we could take this portion here and plug it in there for H, which now means that we have W squared times 72 minus 2W for our volume function that's in terms of the width. And so we multiply this out, and I'm going to use commutative property and switch terms here. We're going to end up with this, which is minus 2W cubed plus 72W squared. Now, just like the last problem, our objective here is that we want to take the derivative of this particular function and set it equal to 0. And we want to do that because we want to find the place or places where we have a local max or local min. And since we want to maximize, we're specifically looking for local maxima. Okay? So here, we just need to go ahead and take the derivative of this. So if we do that, the derivative of V would be minus 6W squared plus 144W. And so now if we set this equal to 0, this would imply that negative 6W squared plus 144W is equal to 0. We factor out a W. And we see from here that either W is equal to 0 or negative 6W plus 144 is equal to 0. And from here we can add 6W to both sides. divide both sides by 6, and what we end up with here is that W is equal to 24 inches. And so this would be our W max here. Now, one of the things that we need to consider here is that we know that for the measurement of the length or the width, we know that all this has to be greater than 0. So here, because of that, we are going to ignore this particular solution, okay? Because it does not make sense to us. The only one that does make sense to us is this solution here, okay? And so now that we have that solution here, we know we know 2 of the 3 dimensions already. And so if I'll just come over here and do dimensions. So we know we have 24 inches by 24 inches by, and then we'll find out the last number here in just a second. So we have our W's. Now we need to find H. So H here, it'll come back over here. So H max is just going to be whatever this was, because remember we wrote H as 72 minus 2W. So that's going to be 72 minus 2W max. And so that's just 72 minus 2 times 24, which is 72 minus 48, which is just 24. So we see here we have another 24 inches there. And so of course, with the dimensions being 24 inches by 24 inches by 24 inches, the area, of course, is going to be all this multiplied. We could stick it back into this formula here, but it'll still end up giving us the same thing. So it'll be 24 inches and all that cubed. And when we calculate that, we end up getting 13,824 cubic inches. So I'll go ahead and write that in here. So now we have our dimensions as well as our area. And so finally we'll go to our last example here. So for this one, we're dealing with related rates. And so here we are assuming that we're pumping gas into a large spherical balloon. So the balloon looks like a sphere. And we know that its volume is increasing at a rate of 5 cubic feet per second. Okay, so here let's do a little background. So we know that the volume of a sphere is V equals 4/3 pi r cubed. Okay, and when we read this, volume increases at a rate of 5 cubic feet per second, we know that we're talking about the rate of change of volume with respect to time. And so they're saying that that's 5 cubic feet per second. Okay. We also want to know what is the rate of change of the radius when it is 4 feet large. So here we know our radius is going to be 4 feet. Now if we look at this function here for volume, if we wanted to take the derivative of the function with respect to time, because that's what we're given here, we have a bit of a problem because volume is written in terms of the radius. So what we would have to do is do implicit differentiation, aka applying the chain rule. And so in doing this, if we wanted to take the derivative of this function with respect to time, we would actually have to do it this way. Okay? And so here, this says what is the rate of change of the radius when it is 4 feet large. Okay? So this part relates to the radius, but this part here, rate of change of the radius, is asking us about this portion here. So that's what we're actually trying to find. So what we're going to do is do implicit differentiation on this particular equation here, and then from that find out what we need. So we come here and we say dv dt is equal to dv over dr times dr dt. Okay, and so coming here, we know that this portion here, we just need to take the derivative of the formula for volume times dr dt, and we know that this value here, the dv dt, is just 5. Now we actually take the derivative of this, and we get 4/3 times 3 pi r squared times dr dt, and that reduces down to just 4 pi r squared times dr dt. And if we divide both sides by 4 pi r squared, we get dr dt is equal to 5 divided by 4 pi r squared. Okay? Now, we're almost at our answer here. So we know that our radius here is 4 feet. So now what we need to do is say when r is equal to 4 feet, then we evaluate this and we just plug in 4 into the equation. And so once we do that here, you'll see that we just multiply the bottom or the denominator, and that will be 1664 pi. So it'll be 5 divided by 64 pi, and I'm going to go ahead and work that out right quick. And when we do that, that ends up being 0.78125 feet per second. And so that is the units there, because remember, we're doing radius with respect to time here. And so radius is in feet, time is in seconds. And so you see here, our answer will be, if the spherical balloon's volume is increasing at a rate of 5 cubic feet per second, when the radius is 4 feet large, then that means the radius is increasing at a rate of 0.78125 feet per second. And so with this concludes the video for this week. If you have any questions, please ask.